Hello. Today we'll talk about the surface areas of cylinders and prisms. This, remember, is a prism. We have these two rectangles, congruent rectangles, form parallel faces. And I'm pointing to these two. In the case of this box-like thing, there's quite a few rectangles which are congruent and parallel. I just picked these two, here and here. What happens if we were to cut this open? For instance, if I cut it right along this edge right here, and then this edge, and this edge, and along here and here, so that this end that forms one of the parallel congruent rectangles would just drop down like this here. Same thing here. We cut this here, here, and here. Leave it connected right here. It would drop down and look like this. And then if we made a cut right along this edge, this side here would just drop down like this, and these would all unfold. This is the top part that we're seeing right here, and this is this side here. This chopped up version of this thing, which we can then lie flat, this is called a net. It's a relatively new word in mathematics. You can look up, if you can find an old math dictionary, you won't find this word in it, except as it applies to business. The more common usage for the word net is what's left after all the expenses and deductions are taken. Net profits, there's net payroll. That's what's left over after everything else is taken out. This word has nothing to do with that. This is an entirely different kind of net. It also has nothing to do with the kind of nets you catch animals in either, or the kind of nets you catch acrobats in. This is completely different. It involves taking a polyhedra, or actually you can do it with a cylinder also, and cutting it up in a way that you could lie it flat. The cool thing about nets, we don't have any equations involving nets, and I don't think there's even any theorems involving nets. All you have to do is get used to visualizing and going back and forth. This is the net version of this prism here. Throughout this chapter you should see other nets, and the way they turn up on your state exam is normally in terms of identifying the net. For instance, you could look at this, now that we've seen what it is, or maybe you could have done it anyway, and realize that if you folded this part towards this line, and then folded this one up, then flip these two up, you would end up with this. That might not be immediately obvious. My advice for getting good at these things on the state exam is just study them. Look at the nets and the three-dimensional and get used to identifying what it is. So you'll see nets for cylinders, for tetrahedrons, for square pyramids. You can go online and look at a whole bunch of nets and draw them in your notebook and study them. That way you don't have to think about it too much. When you see it on the test, you will just immediately spot what kind of a net it is. And if you're super good at visualizing things, well, good for you. This kind of stuff is just made for you. Because, like I said, no equations, no theorems. It's just a matter of visualizing what this would be if you folded it up. And that's what a net always is. And let's look at a different net. Well, here's something that's not a polyhedron. This face is a circle, not a polygon. And of course course this part here, this is all curved. What would the net for something like this look like? Well, if you were to take a tin can and some snips and slice it right down the center, well, it doesn't have to be the center, just slice it from top to bottom in a nice straight line and then unfold it, you would get this rectangle. And by the way, don't do that with a tin can. Tin cans produce really sharp, jagged edges. If you tried to do this, well, all I can say is take lots of Band-Aids and antiseptic with you, because and some cleaning materials too, because you'll end up bleeding all over the desks and the rug. Something like this, use cardboard or paper. Or wear steel gloves, maybe. Do they make steel gloves? I don't know. The other way to see this, that might be less likely to take your fingers off, would be to start with the rectangle. Like, say, a piece of paper from a notebook, 8.5 by 11 maybe. Well, if you look at it that way, everybody who's ever picked up a piece of paper and over the age of maybe 2 has figured out that you can roll this paper up into a cylinder. It won't have the top and the bottom closed off. It'll be like an open cylinder. But I think everybody knows that you can just roll this up into a cylinder. No problem. So you can unroll the cylinder into this. Well, that takes care of this side here. What about the tops? Well, so if you were to unwrap the cylinder, this is what you'd end up with. A rectangle, which represents the middle part, and then the top and bottom, represented by the 2 circles. The reason nets are kind of useful is that if you can lay something out like this, a lot of times you can just visualize it in your head, but you don't have to. If you can lay out something like this, now you can figure out what the surface area is. We haven't actually defined surface area yet, but we will in a second. In fact, what the heck? Let's do it right now. Let's take something like our box that we had a minute ago. The surface area is just the area of all the faces added up. Just like when we had a polygon, we would take all the sides and add them up, and that gave us the perimeter. Now we're going to take all the faces, add up their areas, and that will give us the total surface area of the object. For instance, here we have this top part. So that would be A sub t, say. And then we have the bottom. And we have these other 2 rectangles, the one behind and the one in front. And then we have 2 other rectangles at each end. So we've got 4 and 2 is 6 polygons. All we have to do is compute the areas of all 6 and add them up. And that is our surface area. And we're going to do that in the problems. We do the same thing here. We would take the height of the cylinder, h, say. How far around is this? Well, if we call this h, distance from here to here, 2 pi r. Because remember, this thing wrapped all the way around this circle here, and we just unwrapped it. Again, think of it more as a piece of paper that we will have to visualize cutting your fingers when you unwrap it. The length here is 2 pi r. So what's r? Well, we don't know yet, but it is the radius of either one of our top circles here. It's 2 pi r all the way around, and that's exactly how long this rectangular piece would have to be to come all the way around this circle. So h times 2 pi r would be our area here. That's the area all the way around. It may not be immediately obvious that this is the best way to do it, but if you think about it, you can see it's kind of simple. When you unwrap this, all you have to do is figure out the area of a rectangle. Even though it's curved, turns out that's okay. just picture yourself unwrapping it and lying it flat, and now you've got a rectangle. Well, for the two circles, we get pi r squared in each case. So, what's the surface area? It's 2 times pi r squared, that's the top and bottom circle, plus h times 2 pi r. This is one area, this one here, and then this is this, jeepers, circle plus the circle here. This part represents, of course, the rectangle, h times the length here. For this, well, let's see here. We have length from here to here, width, we could call that the width from here to here, that's this part right here, and then the depth or the height, whichever you like to call it. Let's call it the height. Well, let's see, this top part, this would be width times length, right? We can write that up here. And this bottom part is exactly the same, so it's 2 times that. What about these sides here? You got this one in front and then the other one in the back here. Well, that's h times L. But we got 2 of those, don't we? And last, we get these, which is W, that's length here, and H. And there's 2 of them. And that whole thing would be the surface area. It's 2 times the width times the length. That's this top part here because there are 2 of them and they're congruent. 2 times the front and the back rectangle, and then the 2 end rectangles. See, it's pretty easy. If you can work out the surface area of our simple figures, in this case it was a polygon and a circle. Here, they're all polygons. In fact, they're rectangles, which is even easier. And that's all the surface area is. You just add up the area of every face that makes up the polygon, or in the case of, pardon me, the polyhedra, in which case you're going to add up the area of all the polygons, or a non-polyhedra. You still just add up the areas of the surfaces. In this case, it unfolds into a rectangle plus 2 circles. And that's one thing nets are good for, to help you visualize what the surface area would be. If you unwrapped it, it's real easy to see what this is, especially in the case of a cylinder. With the box, well, we saw the net of this thing earlier. I'm not sure it's all that hard to visualize in this case what the surface area would be, this part here. In the case of a cylinder, it kind of helps to unwrap it and realize that the major part of the cylinder is really just a rectangle that's wrapped around these 2 circles. Well, here's a net of a solid. We're supposed to figure out what that solid might be, and then find the surface area. Well, since we have all polygons laid out here, first off we can say we have a polyhedra. Now what kind of a polyhedra might we have? Well, we got a triangle. In fact, it's an equilateral triangle at each end. After all, if we start folding these up, these 2 are going to be the ends. We have 3 rectangles here. For a triangular prism, that's exactly what we need, isn't it? We've got a rectangle on this end. We've got a rectangle. Yeah, that's not what I meant to say. We have a triangle at this end. We have a triangle at this end. We're going to need 3 rectangles to connect them. One to connect this side to I think, this side, and one to connect this side to this side. And of course this one right here, which is going to connect this part to this side to this side. We did that previously in the last video, where an octagonal prism would have the two octagonal faces, and then 8 rectangular faces which connect up the sides of each of the octagons. Here we have 3 rectangles which connect up the sides of our 2 triangles. Well, okay so far. Since this is equilateral, these are all 8 centimeters. So for the area of this, we need the altitude times the base times 1/2. Remember, that's the formula for the area of a triangle. Our altitude is 8 squared minus 4 squared. Remember, we just draw a little right triangle here. This is isosceles, so we just finish this off here, produce a perpendicular bisector. This is 4, this is 8. We need to find the altitude here. It's 4 times the square root of 3. So for the 2 triangles, that's 2 times, this is the area for the triangle, 1/2 times 8 times the altitude, which is 4 times the square root of 3. And this here, well, we've got 8. Each of these is congruent. They have to be because they have to match up with each of these sides here when you fold it up and put it together. So each of these 3 rectangles has a width of 8 and a length of 20. And as I said, there are 3 of them, so we get 3 times 160, or 480. Now, if you grab your calculator, all this stuff works out to 55.43. This is 480, you add them up, 535.43. And that will give you the total surface area for this particular prism. Well, here we have a pretty simple problem. We just did that. Find the surface area of the cylinder. We need to find the area of the top and bottom circle, and then the area of this thing when we cut it and unwrap it into a rectangle. Well, this thing, when it's unwrapped, would have a length of 2 pi r and a width of 8. So we want 2 pi r times 8. That'll give us the surface with a large rectangle that makes up the body of the cylinder. Now the top and the bottom, well, that's just 2 times pi r squared. So let's see what they did here. Here's the 2 pi. Well, looks to me like 6 is the length of this segment here. That'll be a diameter. We want the radius. So we want 2 pi times 3 times 8 plus 2 times pi 9. That's 3 squared. So it looks like he used 6 for a radius, or she. Well, if we cut the diameter in half in order to get the correct radius, which is 3, we can pull out the 2 pi, our distributive law, to make this a bit simpler, and make it 2 pi times 24.9, pardon me, 24 plus 9. 33 times 2 pi, or about 207. The answer is significantly different. Of course, when you use the wrong numbers, you really can't expect to come up with the right answer. They show this a lot because it's an easy, careless mistake. Frankly, anybody could have made this mistake. Not because they don't know the difference between a diameter and a radius, but it's easy to spot the 6 and then just start plugging it into your formula without thinking too much about what you're doing. That's what happens when you're in a hurry. You've seen me make those kind of mistakes lots of times, and I'm not even in a hurry. I'm just a little spaced out. Now here we've got a prism. It's made from a right triangle. It's a triangular prism made from a right triangle. They want us to, I think they want us to find the surface area, don't they? Yeah, find the surface area. And they say sketch the prism. Well, since we've learned about nets, I don't see the point of sketching the prism. The whole purpose of this is to find the surface area. And the cool thing about nets, if there's anything cool about them, is that they make it immediately obvious what the surface area is once you've laid it out. So why don't we just produce a net and sketch the net instead of the prism? That's what I would do. Makes more sense to me. If what you're looking for is surface area, why do you need to draw a three-dimensional prism? Draw the net. In this case, I think it's easier to draw the net with the triangles on each end. Just let them come right along with it as you fold it up. I don't see anything wrong with that. We have the hypotenuse and one of the legs. We don't have this one yet, but that's pretty easy, right? That's just going to be 15 squared, which is, I guess, 225 minus 81. The square root of that would be this leg here. So we can work this out and we end up with the square root of 144, which we know is 12. So this leg here is 12. What about these other sides? Well, when we fold this up, remember this triangle is going to be folded up so it's sticking out of the page here. When we fold it, this side is going to have to match up with the hypotenuse right here, isn't it? So that makes this one 15. And this, well, that'll finally have to match up with the shortest side here. And this is definitely not to scale, obviously. If this is 8, how could this be 9? If this is 9, how in the world could this be 8? I exploded the rectangles in between so we could have lots of room to draw in numbers. The actual net would be much shorter than this. As long as we got the numbers, we can work everything out. For instance, this triangle, well, it's going to be, we could say this is the altitude and this is the base, or the other way around. This is the base, this is the altitude. Either way, it's 1/2 of 12 times 9. Same thing over here. So, first off, for the two triangles, we get 2 times 1/2 of 12 times 9. Now, we also have some rectangles. Those are going to be easy. Now that we've figured out what each of these sides has to be, we have 8 times 12 for one of them, plus 8 times 15. As a matter of fact, these are all going to get multiplied by 8, aren't they? They all have the same length. So let's make use of our distributive property and say it's 8 times 12 plus 8 times 15 plus 8 times 9 is the same as 8 times 12 plus 15 plus 9. Well, this part here, for the two triangles, we get 2 times 1/2 of 12 times 9, which of course is just 12 times 9, that's 108. This one, well, these all add up to 36. Multiply by 8 and get 288. We add up the two triangles plus the 3 rectangles and get 396 square units. I don't see the point of sketching the three-dimensional prism. If you want the surface area, sketch the net. Gain a proficiency with recognizing what the net would look like, and when you lay it out this way, I think it's super easy to see what the surface area would be. This is very much like problems we worked in the previous chapter, where we laid things out like this and said what's the total surface area, and then we had to find the area of squares, rectangles, and triangles that were all put together to make the two-dimensional figure. Well, that was preparation for this stuff. What you were doing before is exactly like finding out the total area of this net, treating it as a two-dimensional figure. What's the total area? Now, here's something that looks like it's going to use scale factors. Each side of a cube is multiplied by 3. What is the change in the surface area of the cube? A quick guess would be 9, wouldn't it? We have a linear scale factor, so the areas will be scaled up or down according to the square of this. Let's double check it. Let's take a look at the net of a cube. Well, here we have a net for a cube. We've got our 4 faces here, and then the 2 sides we could fold up. It will close it off into a cube. And they each have, these are all the same square. They're all congruent. That's what it means to be a cube. Let's say they all have side length equal to 1. Well, that means each one of these is 1 square unit, and we've got 6 of them. So we can immediately write that the surface area equals 6. Now, what's going to happen, because that's 6 times 1, okay? Now, if we multiply these by 3, what do we get? We get 3 by 3 here, 3 by 3 here. So each of these is going to now have an area of 9, 9, 9, 9, and there's 6 of them. So we get 6 times 9. Well, that's our original surface area times 9. If you're in a hurry, you might just grab this, because we now know that if you have a linear scale factor, you have to square that to get the scale factor for the areas. If you have the area scale factor, you take the square root. For instance, if they told you that the areas were in a ratio of 9, you would know that the sides were in a ratio of 3. I think to do this quickly, as I say, on a test, by now you could probably just instantly go to the 9 here in like 2 seconds answer this question. I did it this way because I'm not on a test right now, and it's good to see that it definitely does work out exactly the way you would expect it to. For surface area, just like area. After all, surface area is just a whole bunch of areas added up. You already know how to find areas of these things, so the surface area is a very small step forward. Well, this one, after that last problem and what I said, you should be able to just write down 5. What's the square root of 5 squared? The radius and the height, that means our linear parameters have changed by this. So our area, which is a squared parameter, would just move as the square of this, or 5, because this is really a scale factor, the radius and the height of the cylinder. If you don't like that, and they say they're divided by square root of 5. I should have pointed that out. So the change in surface area is to divide by 5. I just wrote it the same way they did, but in reality, your actual change is 1 over 5, isn't it? They divided it by the square root of 5, so you would divide by 5. Or you could say that the scale factor for areas is 1/5. How does that work? Well, we get, for the surface area of a cylinder, it's 2 pi r times h. That'll give us the whole surface of the main body of the cylinder. It's 2 pi r all the way around, and then h units high. And this is just 2 times pi r squared. Well, suppose we divide r by 5 and h, by the square root of 5. Oh, what do we get? Remember, the surface area is the sum of these two things, so we can pull out the 2 pi and write as r over the square root of 5 times h over the square root of 5. This will be our new one. And it's going to be 2 pi times all this, plus 2 pi times r over the square root, r squared over the square root of 5 squared, which is 5. Root 5 times root 5, well, that's 5. So if we rearrange this, we can pull 1/5 out of each of these terms and write 2 pi over 5 times r h plus r squared. And that 2 pi shouldn't be there, sorry. It's 2 pi times r squared over 5 and rh times the square root of 1/5 and the square root of 1/5 down here. Well, 2 pi times rh plus r squared, that's the surface area for a cylinder. So if we take that cylinder, divide the linear parameters by the square root of 5, we get our original area all divided by 5. So this is just straight from our previous sections using scale factors and similar figures. In other words, you pretty much already knew how to do this. You just didn't know that you knew how. Well, I don't see anything wrong with sketching what's going on. And remember, a net is just a simple way of laying out flat all the things that make up the surface of the figure. Of course, in the cylinder we get these circle top and bottom and this rectangle here. And all the cylinders we've worked with so far are right circular cylinders. And the only difference would be this. I'm not very good at drawing odd circles, but suppose that's it. Cheapers. Suppose the angles here, like this, are not right angles. In other words, we take an ordinary cylinder and cut it in an angle, not horizontal. Let's say these two lines are vertical. Instead of cutting it horizontally, the kind of cylinder you're used to seeing, we cut it at an angle. Kind of like if you took a straw and put your scissors at an angle and cut it, you end up with kind of a sharp point at one end, and then cut it again at another end at exactly the same angle. Then you end up with a cylinder that's not a right cylinder. Most of the cylinders we'll work with, I hope, will be right cylinders. They're much easier because you have this nice little rectangle going on down here. Well, they tell us the radius is 4 feet. Tell us the height is 10 feet. Not much of a scale, is it? Well, then what's the length from here to here? Well, remember, it's 2 pi r, just the distance around the circle, because this rectangle has to wrap around this circle. Now, in this case, that's 2 pi times 4 would be the distance from there to there. So the surface area would be 2 times pi 4 squared plus So if we lay this out, we get 2 times pi r squared, which is pi 4 squared, plus 10 times 2 pi r, which is, turns out to be 25.1 for this length here, 2 pi r. To get the whole thing, if we don't want to do it separately, we can pull out a 2 pi 4. We've got 2 pi 4 here and 2 pi 4 times 4, right? Because that's 4 squared. So we can pull it out and write 2 pi 4 times 4 plus 10, which is 8 pi times 14, 351.7. That's what you get if you take this, and we should get about 251 here for this area, and each of these is about 50.24. There's some round off error. Well, pardon me, this is 251, jeepers. But not much. This is 2424 is 0.5 plus 1 is 0.6. Yeah. I think I mentioned before, I always use 3.14 or 6.28 for pi, or 2 pi. If you have a pi button, maybe your answer could be a few hundredths different from mine. You're not wrong. In fact, probably I'm wrong, because I use the approximation for pi. I hardly ever use the pi button. Next question. If you can double the height or double the radius, which will create a greater surface area? Well, doubling the height would double the surface area of this rectangle. And if we double the radius, we'd be multiplying this 4 by 2, which means we'd multiply the whole thing by 2. In that case, we would also double the area. So whether we double the height or the radius, we double the area of this thing, and it makes no difference. However, for our circles, the height doesn't even enter into it, does it? The height has no effect on the area of these circles. And in fact, when you double the area, or pardon me, double the radius, you square the area. Or it moves as the square of the radius. So obviously, it seems pretty obvious to me, when you look at it that way, the radius is the thing to increase, because it enters into all the area calculations, the circles and this rectangle, whereas the height only enters into one of them. Well, we can try it and see what happens. If we double this, what will we get here? Everything else would be the same. We just get 4 plus 20 over here. So if we doubled the height, let's say, well, we double the height. Let's just leave it at that. So this is 24. We get 8 pi times 24, and that'll be 2 times 351.7, around 703 or 2, something like that. I think that's about right. That's roughly what we get. However, if we double the radius, let's see here. We'll get, let's do it down here. Don't get these confused. For our rectangle, we just get 2 pi 8 times 10. And if we do the math, it turns out just like what we expected. We double this, our new surface area goes up to 703 from 351.7. But if we double the radius, we're up to 903, which is definitely bigger than 703. So, just like we thought. It's the radius that we want to double. And part C, well, okay, I guess we just did that, didn't we? Just always remember to keep straight the differences between linear dimensions and areas. Areas always come from multiplying two linear dimensions, which means when you change the linear dimensions, if you change both of them, you change the area by the product of the change. For instance, if I double this, and, pardon me, suppose I had a box. Well, okay, a box that got kicked in the side there. That's just a side view. Well, if I double this side and triple this side, I'll get the original area times 6. Multiply this side length by 2 and this one by 3. I will multiply the area by 6. And of course, if these were the same, for instance in a similarity transformation, if these were both 2, then it would be the area times 2 squared. If these were both 3, it would be the area times 3 squared. Well, that's about it.